Hi, everyone. I am going to talk about red-black trees and their applications for my final project. And before I can get into red-black trees, I will give you somewhat of an overview. Basically, what it is that all the nodes in the tree are either colored red or black. It is used because we want to make sure that every path from root to leaf are in such a way that the tree is balanced. And we have node attributes, which are color, key, left, right, and the pointer. I want to talk about 5 properties first that are very essential to red-black trees. Either node is red or black, yes, as I've said before. The root is black. Every leaf nil is black, which is what you see on the bottom rightmost hand side of the screen. You see all these nils. You see 3 is a parent of 2 nils, 7 nil is a right child of 7, 12 has 2 nils, and so on. And if a node is red, then both of its children are black. We also need to keep in mind that all paths contain the same number of black nodes. So this is something that I call the black height, which is a number of black nodes, not including node X itself, down to the leaf. We also have a lemma, and the lemma says a red-black tree with n nodes has a height of at most 2 log n plus 1. We do have a new vocabulary word. It's called sentinel. You can think of sentinel as this t.nil on the bottom of the screen. Why we use it is because we want to consider every node that points to a null as the parent node. So 3 is a parent node of t.nil. 7, t.nil is the right child of 7. 12, 15, 16, t.nil is the right child. T.nil is a left child of 19. We have 20, 23, 28, 35, 39, 47, even 26. So this t.nil accounts for all of the nil children. So it is a cleaned up version as a picture you saw before. Before I can get into operations, I want to introduce a concept called rotation. So you can either do a left rotation or a right rotation, but we want to satisfy the binary search tree property. Keep in mind that we saw that in class. If y is a node in the left subtree of x, then y dot key is less than or equal to x dot key. If y is a node in the right subtree of x, then y dot key is greater than or equal to x dot key. So let's say we have this tree here on the right, and we have node x and node y. Node y is equal to 18, node x is 11. And we want to perform a left rotation. How we do a left rotation on the pseudocode on the left is that we're setting y equals to x dot right and essentially turning y's left subtree into x's right subtree. We do have an if statement that links x's parent to y. So we're setting y dot parent equals to x dot parent. We also have another if statement, and this is where we see that x is on y's left. So that's why 11 is on the left side of 18. So it's a left child of 18 once we do that left rotation. We do have a concept called RB insert. We did learn something similar called tree insert in class. Now I won't be going over the full details of this pseudocode, but I want to make sure I emphasize that nil in our tree insert is replaced by t.nil. How we did tree insert was that we found a node with at most 1 child, and we made it the parent of z by walking down the tree from the root. So in this case, what I will mention is that we also have to replace z dot left and assign that, not replace, I mean assign that to t dot nil, and assign z dot right equals a t dot nil, and we are making z dot color to be red. We also are calling this algorithm, it's called RB insert fix up. I will get into it in the next slide. Its main purpose is to recolor the nodes so that they are satisfying the red-black tree properties. Before I get to that though, insertion costs big O of log n time, because we're looking at the height of the red-black tree. So if the height has n nodes, then it's big O of log n. As I promised, RB insert fix up it's 16 lines, so it's not that long, but there are 3 cases to consider. The first case to consider is that the inserted node Z has an uncle called Y, and Y is red. The second and third case, the uncle of the inserted node are both black, except in the second case, the inserted node is a right child. The third node, or the third case, is the inserted node is a left child. So you will see this in case 1. We can go over first in this example. So we're trying to insert Z, and B is red, but so is his parent. This is violating property 4. We can't have them both red. So what we do is we recolor node A to be black, and our new Z is pointing to C, which is now red, and D is now black. In part B, Z is a left child of B, so they're both red, so property 4 again is violated. And also its uncle is red. Its uncle is D, which is Y. So what happens is we end up coloring B black, A again stays red. Our new Z is now red, and D is black. So case 2, we recall that the uncle of the inserted node is black, but the inserted node is a right child. So the inserted node, and that you can't really see the uncle in this picture. This picture is from the book, but we do see property 4 being violated. And in case 3, we see property 4 violated again, as is the subtrees. We're looking at alpha, beta, gamma, and delta. They all have to have the same black height, which is the number of black nodes. So when we do, how we get around this, if we're in case 2, is we have to perform a left rotation. And if we're in case 3, we have to do a right rotation. And in both cases, we get this bottom right picture, and we see that all of the subtrees, alpha, beta, gamma, and delta, are all the same black height. And we have B is up top here, and this is black, and A is red, and C is also red. It is important that I go back for 1 second and note that more than 2 rotations is not done, since a while loop terminates if case 2 or 3 is executed. The while loop, I should say, is under the assumption that Z.P, the parent of Z's color, is red. If it's not red, then the loop will not run. And on line 16, the last line, T.root.color is equal to black. So insertion, I said, costs O big O of log n. So does insert fix up. I now will talk to you about RB delete. RB delete has two concepts. We didn't really learn this in class, but I will go over them, being that their algorithms are very small, but essential to RB delete. The first one is transplant. Node U's parent becomes node V's parent when we replace node U subtree with the subtree of node V. And tree minimum returns a pointer that points to the minimum non-null element in the subtree. This algorithm is 22 lines long. And like I said, as with insertion, delete has a fix up as well. Before I get to that though, deletion costs the same time as insertion, big O of log n. RB delete fix up has, it looks a little intimidating because we have 4 cases. The first case is that X's sibling W is red. So W needs to have black children. If it doesn't, then we have to switch the node colors of W and X's parents' colors, and then perform a left rotation on X's parent. In case 2, X's sibling W is black and both W's children are black. In this case, we change W to red and we do a second iteration of the while loop, setting X.parent equal to the new node. The while loop is running under the assumption that X is not equal to T.root and X.color is black. So both of those conditions have to satisfy in order for this algorithm to run. In case 3, we have X's sibling W is black and W's left child is red and its right child is black. In case 4, X's sibling W is black and W's right child is red. In case 3, we have to right rotate W and swap W and W.left's color. In case 4, we have to left rotate X.parent. The while loop terminates when we set X equal to T.root. A better way to illuminate this, these cases are by first starting with case A. X's sibling is W, W is red, and it has 2 black children, C and E. We have to exchange B and D and left rotate. When we perform the left rotation, B is the left child of D, and D is now black, and B is now red. X stays the same as A, but our new W is now at C. For case 2, which is B, we have this, I should say this in advance, that this B over here can be either red or black. The book doesn't color it, which is why I left the color, this neutral gray color, because it can be either red or black. So in this case, the pointer moves up the tree when we color node D red and set X as the pointer to node B. So our new X is B, so it went from XA to pointing to B. Also, D is now red, and we need to check for case 3. Case 3, if you can remember, X's sibling W is black and W's left child is red and its right child is black. So its left child, W's left child is C. Its right child is black, which is E. X is over here. X's sibling is W, which is D. And we again have this B, which can be either red or black. To get around this case, we need to right rotate C and D. So we're performing a rotation here. When we perform our rotation, D becomes the right child of C, and C is the new W. Also, the colors are changed. C is now black and D is red. In case 4, we have X's sibling W. It has a right child that is red, which is E, and C can be either red or black. In this case, we rotate B and D. So here's B and D, and B now becomes the left child of D, and B is black, and E is now black as well. We also need to keep in mind that alpha, beta, gamma, delta, epsilon, these all have to have the same black height throughout all the different cases. We're trying to get them so that they are equal in black height. I also should mention that on the last line, X dot color equals black. So we're setting X dot color equal to black. There are some improvements to RB trees. The first improvement is ABL tree, stands for Adelson, Belsky, and Evangeni Landis. So in this case, for each node, the height of the subtrees differ by at most 1. We have to apply X dot H, which is a new attribute accounting for the height of the node. Our pros of this is that searching a tree is faster since it's more balanced than a red-black tree because the height of the subtrees differ by at most 1. The cons is that it needs extra storage. Obviously, if we're applying X dot H per node, it's going to cost more in storage than the red-black tree, which is storing color, its left and right and pointer. Our second improvement is trees. What does trees sound like? Trees sounds like heaps, and heaps we learned in class. I will give you somewhat of a warning. This is a picture in our textbook. It does not account for ordering in the different numbers. 73 is up top and should be in G spot since it's the largest, and 23 should not be the right child of 7. So you can think of this picture actually having the numbers more satisfying the heaps property. However, I should say that trees orders nodes, meaning that it gives a node a random number from a random number generator by using X dot priority, the book calls it. So one of the pros is that if we have a node that was assigned a large number by the random number generator, we can insert it into the binary tree without having to rebalance a tree. Our cons is that the insertion, once you insert a node, you have to account for all of its descendants. You have to update those node numbers. And there might be a small probability or chance that 2 nodes are assigned the same number. So that's something to keep in mind. Like, you have to keep track of the node numbers so that, no 2 nodes have the same number. But ultimately, this is very exciting that these can improve red-black trees. If you're someone who really likes this topic, I strongly encourage you to read more about this online, or you can even email me and I'd be more than happy to talk about it with you. But I hope this presentation really helped change your perspective of red-black trees. And I hope everyone has a great summer. Thank you.